Hey everyone, welcome to Lambda School's Mini Bootcamp. We are now on night 11 of our 12-part Mini Bootcamp. So we are just about to round out the end of this bootcamp. I've had a great time teaching you guys. I hope you guys have been enjoying and learning a lot and have been challenged in fun and interesting ways. And I'm looking forward to our last two classes. Tonight we are going to learn all about recursion, which is my absolute favorite JavaScript topic. So I hope that you guys enjoy it as well. So if anyone is joining us for the first time, my name is Deandra Ryan Moss, and I'm an instructor here at Lambda School, and this is our mini bootcamp. So Lambda School is a 6-month program in which we get new programmers ready to jump into the industry. So it is a complete computer science and web development immersive. As I mentioned, it's six months long full-time or a year-long part-time in the evenings. And we cover front-end JavaScript, back-end JavaScript, a number of frameworks, and then we also look at some computer science topics, such as learning the languages of Python and C, and algorithms, data structures, that type of info. So a really comprehensive course. As well as having an awesome curriculum, we also have an awesome tuition model, which is that if you do not want to pay us anything up front, you don't have to. We have an option where you can pay back your tuition to Lambda School over the first 2 years that you are hired in the industry. So if you get hired, we get paid. If you don't get hired, we don't get paid. So our job is to make sure that you absolutely get that full-time web development job making $50K or over, or else we don't get paid. So that is a nice little option we have to make sure that our school is open to everyone who wants to learn and is capable of learning regardless of current financial situation. This mini bootcamp is our way of getting you guys ready to jump into the main curriculum. So it's the 3-week-long course in which we just touch on the fundamentals of JavaScript, CSS, and HTML. So just introducing you guys to a lot of the different topics that you'll dive into full force in the main curriculum. As mentioned, we are on evening 11 out of 12, so we are almost done here. If you are new to the bootcamp, this probably isn't the best time to jump in cold, but we have all our lessons posted online. So you're welcome to go watch old videos, or you're welcome to sit tight for a few weeks and join us in May for the next time we run through it. So without any more delay, I will go ahead and get us started for today. As mentioned, we're going to be talking about recursion today, which is kind of our final topic in which we see a way that functions can function in really neat, interesting, dynamic ways in JavaScript. So I'm going to go ahead and share my screen, and then we can do a little recap of what we saw last night, and then we'll start to explore recursion. So hope you guys enjoy yourself. Definitely code along, and I'm always looking in Slack, and I'd love to answer your questions at the end. So give me feedback as I go along teaching and help me clarify things at the end. All right, let me share my screen for you. Okay, first of all, I want a little bit of a review of scope and closure, which are the two topics that we learned last night. So the first thing we learned was scope, which is, sorry guys. I'm having trouble getting Replit to cooperate. Here we go. All right, so scope is something that exists in a function. So if I create a function called test function, once I declare this thing, there is scope that exists within these two curly brackets. So for example, any arguments that are passed through are only possible inside the function scope. So if I wanted to console log the argument here, that would be completely valid. If I wanted instead to console log it down outside of the brackets, it wouldn't work because outside of the function scope. As well, any variables that I declare here exist within the function scope. They're accessible as long as they're inside of the function, but once we get down here, it's as if they didn't exist. In fact, the only way to value out of a function is for is a return statement. So if we want to get a variable accessible outside of a function scope, then we return variable. So one more piece of the scope is that it only goes one way. So while anything inside of the function is not accessible outside, the opposite isn't true. So out here we have the global scope. And oh, I'm getting some feedback that we're having trouble with connection. Let me see if there's something I can do to speed it 1 second. Sorry about that delay. Hopefully I've been able to resolve the problem and you guys are able to hear / see screen share. So let me go back to talking about scope a little bit here. So out here in the global scope, we have a variable. This is available anywhere global as well as inside of the function. So we can use global variables inside of the scope, but we can't use function variables globally. So that's a little view of scope and how scope works. Now let's talk a little about closures. So closure is when we use return function to basically save a hidden out of sight. So if we have feedback, audio and video are still, let me try one more thing for you guys. Thanks for bearing with me. All right, I tried one more thing, and hopefully this will solve the issue. So I'm going to back in this idea of closure and definitely keeping me feedback in Slack if we're still having problems. So now I'm going to do a little bit of what closure is. So if you have a function, I'll use the example of doing a bank lookup, just something we saw last night. So if you wanted to have a Hey guys, I'm back and hopefully everything is resolved. Thanks for bearing with me tonight. Sorry about the technical issues. Sometimes it just happens with these online lectures. So I'm assuming everything is back and good to go. Please let me know in Slack if we're having any more issues. I'm hoping we got it resolved though. All right, so I was doing a little bit of a review of closure and scope from last night. I'll just do a quick little review of what closure is, but we might have to kind of skip over that part so that we have enough time to get to recursion. So hopefully everything is working and you guys can see and hear me so that we can learn all about recursion tonight. I will go ahead and share my screen again. Okay, sounds like people are giving me good feedback about the connection. So hopefully it will be smooth sailing for the rest of the evening. So let's talk a little bit about closure. So we saw an example last night about using closure to store bank account info. So for example, if you wanted to have some sort of lookup system where someone enters in, so if we start out with some sort of bank account object that contains a series of passwords and account numbers, we'll make up a couple mock account numbers, and then we'll do for 2, etc. All right, so we have this object with bank account info, and then let's say we have a function where we enter in a password and it returns for us the account info. So right now this totally works. If I use get bank account and entered in my password, I would be able to get the account number out. But this isn't a very good system because this bank account object exists globally. It's in the global scope, which means anyone can see anything in it. And we don't want you to be able to see everyone's account info, just yours. So in this case, we could wrap everything inside of a closure. So we could create a larger function called in which we actually pass in the bank account. Let me switch these around. And then instead of declaring this function, we could return it. So in this way, somewhere behind the scenes, we could use the account generator with our bank account object and save this into a variable called getBankAccount. So the reason that this would be useful is that presumably this logic is happening behind the scenes. So then what will be publicly available is just this getBankAccount function. And so now this thing has a closure with our bank account so that, I'm missing a bracket somewhere. Let's see. Oh, right here. Okay. So now we have a closure that's been generated between this bank account, and of course we could also put it directly in here if we wanted. So now, oh man, I am just, sorry guys, I feel a little frazzled from all the technical difficulties. What have I done this time? Oh, Here we go. All right, so now a closure has been generated within this return function, linking it to this bank account variable. So even though account generator is done being executed, the scope has opened and closed, this bank account variable is still linked to this return value. So in that way, we can do lookups based on the password without having to make this publicly available. So that's a little review of closure and scope, a little bit punctuated by our technical difficulties. But hopefully you guys are getting used to that and not having too much trouble with the homework from last night. I think it is time for us to move on to recursion now. So recursion, simply put, is when you call a function inside of itself. So let me show you what I mean by that with a really simple example. All right, so if I have a function called recurse, so I have a function called recurse, and I'm going to have it do something very simple, which is just console log recursion is cool. So we have this recurse function, and we log recursion is cool. But now we need to actually do some recursing. So right now, this is actually, even though it's called recurse, it's a non-recursive function, which means that it never calls itself. So it works as expected. We see our log statement appear in white over here. But now let me go ahead and add the recursive element. So once again, recursion literally means that we take whatever function we're in, and within that function scope, we call itself. So this thing seems a little crazy and like maybe it shouldn't be allowed, but let me tie this into scope and talk to you why I am allowed to call a function inside of itself. So as we know, out here, we have the global scope. So outside of the function is the global scope, and any variable in the global scope can be accessed within the function scope. So out here in the global scope, notice that we have a variable called recurse. So the name of the function is actually a variable that exists in the global scope, which means it's allowed to be called within the function scope. So if we just had some disembodied variable out here, we know that this thing would be available within our function scope. But it turns out that the same is true of the function name itself. So in that way, we can call a function inside of itself. Now, I will admit that this example that I've put up here, while a really simple example of recursion, is not the best example. And let me break down why. So when I call recurse down here on line 9, it's going to execute everything within the brackets, right? Everything within the function scope will be executed. So we call recurse on line 9. It takes us up here. It'll console log recursion is cool, and then it'll call a second copy of recurse. So now we have 2 copies of recurse being called. We jump back up here, we get another console log, and then we call recurse again. Now a 3rd copy of recurse is going to be called. We jump up here, we console log, now a 4th copy. And I'll save you guys the trouble of me going through this for another couple minutes and just say that there's nothing that will stop this process. It'll just keep calling itself and keep creating new copies of itself. And theoretically, it could do this forever until my computer crashed. But luckily, Replit and most other places that you run JavaScript have built-in stops. So if I run this, we see that I'm getting just tons and tons of copies of this console log. And then finally, Replit throws an error and says maximum call stack size exceeded. That means we have too many functions being called all at once. And this is an infinite loop. You can have infinite loops with any type of loop. You could have an infinite for loop, as we saw. You could have an infinite for each loop. Well, actually, I don't think you could have an infinite for each loop. I take that back. And you definitely can have infinite recursive loops. So you have to be careful with recursion because you want to make sure that when you're calling a function that there's some sort of logic in place to stop it. And we'll see a little more what that looks like as the lesson goes on. The biggest takeaway here is that we can call recurse within itself. And so there's one more thing I want to bring up before we move on to a better example of how to use recursion. And that's that clarifying this idea of when I recurse the first time, I create a second copy of recursion. And when I run it the next time, I create a third copy. So when this function runs, it's not just being called once. So normally in a non-recursive example, when a function's being called multiple times, it looks like this. We actually explicitly on the page call it 5 different times. And we know that while there's just one function called recurse, that 5 different versions have been called. You want to think about it the same way in a recursive case. So down here, when I ran this function wasn't just executing once. It was executing thousands of times. And a way that I like to think about it is with the example of Russian dolls. So in case anyone is not familiar with Russian dolls, they're these weird, creepy little dolls where you have, 5 or 6 or 7 of them, and they all look exactly the same, but each one gets a little smaller so that you can stack them inside each other. And when I was a kid, my mom had some of these, and I was fascinated with them. I would play them all the time. And I think that maybe I was like mentally preparing myself for recursion. So recursion is like Russian dolls because when we first run recursion, we create one copy of the recurse function. When we run it the next time, we create another copy nested inside that first one. When we run it a third time, there's another copy nested. So really, in that other example I showed you where you're just straight up calling them multiple times, it's like one copy runs and then it finishes. Then one copy runs and it finishes. Then the next one runs and finishes. So it's like they're stacked next to each other. With recursion, we actually stack them inside each other. So a new copy of this function starts to run before the original one ever finishes. And once again, we'll look in a little more detail about how that actually looks in a real world example in just a second here. So that is a little intro to what recursion is. And now let's explore how we might actually use it without creating an infinite loop in an example called countdown. So I want to create a function called countdown. And we're going to take in a start number, and we want to count down to 0. So here's how the function should work. If I called countdown of 5, for example, I would want logged to the console 5, 4, 3, 2, 1, 0. So we count down from our start value to 0. If I called countdown of 2, I would want to see 210 logged. If I called countdown of 0, I would just see 0 logged. And finally, if I called countdown of a negative number, I wouldn't see anything logged to the console because we're already underneath 0. So we could definitely accomplish this using a for loop, but instead we're going to use recursion. So for sure, the first thing we want to do is console log our start value. Actually, even before that, notice that in this last case, we don't ever console log our start value because it's below 0. So let's put in an if statement. So if start is less than 0, then we just want the function to quit, right? In this case, we don't want the function to do anything. So one simple way to do that is with a return statement. I know that I've taught you to use return statements to return a value out of a function, and that's often how they're used. But there's another use case for a return statement, which is that if we just want to tell the function to quit, we can throw in a return without any value. So now we know that, and in fact, I'll get rid of this for just a minute. So we know that if start is less than 0, we return. And sure enough, in this case, it'll work. And then in the case that it's above 0, we want to console log our start value. So let's see how we're doing so far. My bad. Right. So this looks like a good start. It's definitely not fully functional, but we see that in the first function call, we were able to get our first value logged. In this call, we got our first value logged. In this call, it actually ran correctly in this case because the only value is the first value. And then we didn't get any log for this final calling. So that's a good start, but we need some way of actually incrementing our values down. And that's where the recursion comes into play. So now I'm going to call countdown on start -1. And that's saying, okay, do everything we just did, but we want start to be 1 value less. So let's see how this works. Looks pretty good. We have the countdown from 5 here, the countdown from 2, the countdown from 0, and then it looks like nothing was logged for this final function call. So even though this thing is fairly simple, it's only a few lines of code, it's incredibly complex. And so I want to break this down in possibly excruciating detail to make sure that you guys understand exactly what is going on here. All right, so let's go ahead and count down. Okay, so the very first thing that happens is we call countdown with the argument of 2. So countdown, the argument of 2. And we can see that it's explicitly stated on line 10. So once that happens, we're now inside of our function. Actually, let me do. Okay, so now we are inside of our function. And so the first thing that's going to happen is our if statement. So we're going to check if start is less than 0, and it's not. So we check if statement, and we see that we skip it in this case. So we skip our if statement. Now we go down to the console log, and we are going to console log 2, because that is what our start value is. In fact, I'll clarify that our argument is called, our parameter is called start. Now we get to line 7. And on line 7, we're going to call countdown. And now our start value is going to be equal to 1 because we did the old start -1. So now we open a new function call. And we go back to line 2. So we look at our if statement. And once again, our start value 1 isn't less than 0, so we skip it. Then we're going to console log 1, and then we hit our recursion, line 7. So now we're going to call countdown with 0, and we jump into another function call. So every time we jump into a new function call, I'm tabbing in. So we go back to the top, we look at the if statement, we're still going to skip it because now, because our start value is 0, but 0 is not less than 0. So we skip it. We will console log 0. And then we hit line 7, and we will actually recurse one more time. So now we're doing countdown of -1. So this is a subtle point because we never see -1 logged, but there is actually a function call for it. So now we check our if statement, and we see that it is true, right? -1 is less than 0. So our if statement is true. We go to line 3, and we return out of the function. So this is, I think, the most important part of recursion and the easiest thing to forget. So at this point, you might say, okay, we hit our return statement. That means we pop out and we're done, right? Actually wrong. So what first happens is we pop out of this function call. There's this function call. So think of this as being our smallest Russian doll. So we pop out, and we're still in countdown of 0. Of course, we were on line 7, so the very next thing is line 8, which is the end of the function. So then we pop out of that. Now we're in this one. And so we pop out, we hit line 8 of this one, we pop out, and now we're on our top call, and we hit line 8 and we pop out. So there's nothing that happens down here after the recursion. So we can't really see this point too clearly in this case, but we don't just return once. We actually have to pop out of every single function call separately. And to make this really clear, I'm going to go ahead and add another console log here. It says leaving function. And then I'll go ahead and just log that start value to really clarify. So, or I'll actually, let's say post recursion. So you see we go in, we have our first function call, we go deeper, deeper, and then we have to pop back out one at a time. And we see that this line 8 has to execute 3 times for these 3 function calls. So once again, this return statement doesn't mean we return out of every single function, we just return out of the innermost function. And then we have to return out 3 more times. And in this case, there's no actual return statement. I could put one down here if I wanted, but when you hit the line of the end of the function, it's the same thing as returning. So using this logic, we can see that we can actually create a count up function really easily just by moving this console log. So now if the console log is after the recursion, count down becomes count up. And if I change this value, it still works. And that's because we're popping into the function one at a time. We're popping into, let's put it back to 2. So we're calling the function once, calling the function twice, 3rd time, and a 4th time. But the console log isn't going to happen where I have it on this diagram. Give me a second to move these. All right, so let's walk through what happens here. So when I've moved this console log, every time it's called, we'll check the if statement, and then we recurse. That's the very next thing. So then we check the if statement, we recurse. Check the if statement, recurse. In this case, with countdown of -1, the if statement is true, so we return out, but this pops us into not outside of every function, but just into this most recent one. So this is countdown of 0. So now that we've popped out, we still have to execute line 7, which is our console log. So we console log 0, then we pop out to the next level, and here we console log 1, and finally we pop out to this top level and console log 2. So in this case, we're actually counting up because the console logs are occurring as we come out of the recursion chain, not as we go in. So hopefully this demonstrated to you this idea of recursion being kind of like a set of Russian dolls. If you put them together, you have to go, if you're taking them apart, you have to start with the biggest one, then the next one, then the next one, etc. But then when you're taking them back apart, you go in the opposite direction. And it's the same thing where we dive deeper and deeper into these recursive calls, but once we're finished, we have to pop back out one at a time. Oh, and I just noticed that Eric in the Slack channel made this observation before we even got to it. So very astute. I see you guys are, at least one of you guys are paying attention. So that's good to know. Also, that probably means that my audio and video are coming through. So a good sign as well. Okay, so let's look at a slightly more advanced case of recursion. So this case is useful in terms of console logging, but we haven't actually, we don't have any return values. So if we want a recursive function that actually returns something instead of just logging, things get a little more tricky. So let me use this example of sum. So it's going to do something a little similar to countdown in that we're going to be thinking of summing down from 5. So, oops, not start. So down here, if I did sum of 5, I would want that to be equal to 15, which is 5 plus 4 plus 3 plus 2 plus 1. And we could do plus 0, but there's really no point. So sum of 5 should give us that result. Sum of 2 would just give us 2 plus 1. And just like in our countdown function, if we did sum of something negative, it would be undefined. We wouldn't get a value back for this case because this function will only be designed to work with numbers 0 or greater, or 1 or greater, either way. So let's write this sum function. So first of all, I want to show you why this is tricky. So we do want to start in a very similar way as we did with our countdown, which is with our base case. So we say if start is less than 1. So this thing won't work for 0, just for positive numbers. So in that case, we want to return. We don't care about writing the function for any start value less than 1. And just as a note, it's this if statement that prevents us from having an infinite loop. So just like in a for loop that you have to say, if I is less than, some value, we prevent ourselves from having an infinite loop with this line here. It's saying, this is our base case or our stop value. It's saying, hey, we only want to iterate as long as I is less than 10. So with recursion, we accomplish a similar task using an if statement. To say, hey, we know we're going to be counting down or incrementing down. So we want to say that once start gets low enough, we need to return out. Otherwise, we get an infinite loop like we saw in that first example. Okay, so what do we want to do here? Well, we want to add things up, right? So we can say, and at the end, we're definitely going to want to return something, like return, maybe if we declare a variable called counter, and then we want to return our counter down here, and then we could recurse. We have this idea that's going to work kind of similar to the last one. So let's say start minus 1. But we have a problem here, right? We're not incrementing our counter. And even if we want to do something like, okay, counter equals counter plus starts, that seems like another step in the right direction, but we're still having some problems. Oh, we want that to be let. So as a reminder of let versus const, once we declare something with the const keyword, it's stuck with that value for the rest of ever. But in this case, we want to use let for counter because it's something that we're going to increment as we go. So let means that our variable is flexible to being changed. So, all right, let's look at this thing. This seems like we mostly have the things in place, but maybe it's going to work, maybe not. So I'm going to try sum of 3. And we get back out 3. That's definitely not right. So we wanted it to be 3 plus 2 plus 1. So we wanted to get 6, but something is going wrong. So in a very similar way, I'm going to walk through this and show you why this example is not working so that we can understand how to fix it. So we start out by calling sum of 3. Okay, so we start out calling sum of 3. We check our if statement, which is going to be false, so we skip it. We declare our counter to be equal to 0. And then on line 7, we increment our counter. So we do counter equals counter plus start. So now counter will be equal to 3. And then we recurse on line 9. So we call sum of, actually, I'm going to make this even simpler and just do 2. All right. So now we're going to call sum of 1. And inside of this thing, we check our if statement. It's going to be false. Now we declare another variable inside of this function scope called counter. We started at 0. We increment it to 1. And then we recurse again. So now we will recurse with sum of 0. So in this case, our if statement is actually going to be true, so we want to return. So remember, this doesn't mean we quit everything. It just means we return out to the next layer. So now we're at sum of 1, and we see that we're done recursing, so now we're on this return statement. So we return the counter. And within this function scope, counter equals 1. So we return 1, but of course that doesn't pop us out all the way. That just pops us out to our next function scope. And over here, we still have to run line 11, which returns counter, which equals 2 in this case. Now we return 2. So when I run this, we're going to get 2. So let's break down what's going on here. So we're declaring a new counter every time. So that means that every time we recurse, we start fresh, we add it up. That's not good because we want our counter to be something that persists throughout all of this recursion. We don't want to start fresh every single time. So that's one thing that we know is wrong with our code, is this line 6. The other issue is this return statement. Notice that here I return 1, but the return statement doesn't go anywhere. That's this line of code. In one case, this executes, or this resolves to the value of 1, but it's not stored anywhere. So we have a few different issues going on here. And as it were, return values can be very challenging when it comes to recursion. So let me show you guys, there are a few different ways to create a function like this, but let me show you a little trick called an inner recursive function that will help us resolve the issues we're having here. So instead of just having sum be our recursive function, let's have sum be our wrapper. So sum is somewhere that we're going to keep track. I'm going to comment this out for a minute. Actually, we'll start fresh. So I will get rid of all this junk code. And then, so in sum, we want to create our counter. So we want this thing to only be instantiated once and to be somewhere that it can be accessed throughout all the recursion. So I'm just going to declare it up here in sum. And of course, at the end, we know we want to return our counter once we've counted everything up. Now I'll create my inner recursive function. So I'll call this inner function, just to be really unambiguous that that's what it's doing. And in this thing, we'll pass in our start value. We'll actually call it I. And this is where the recursive logic will go. So we want our base case. If I is ever less than 1, return out. And then, of course, we want to increment things. So now counter equals counter plus I. And then finally, we want to recurse. So this will work. And the reason is, first of all, that we're not trying to return out of our recursive function, which you can do, but it creates some problems. Instead of trying to return out our values, we're keeping track of them up here on this scope. So sum is never going to be recursed. It'll just be called once. It's this inner function that we're recursing with. So in this way, we can recurse all we want without having to worry about overwriting the value of counter. It exists outside of the recursive function scope, so we know that it can safely be modified without the recursive function overwriting it. So let's test this a couple times. Make sure it works. Uh-oh. Well, I have done something wrong here. Oh, and of course, we have to actually invoke inner function. So right now, I've just declared it, but it's never being called. So over here, I invoke it with my start value, and now this is going to work. Okay, cool. So we got the expected value there, got 15. And if we do a negative, right now it's set up so that we get 0 for a negative. We could add a little if statement up here if we wanted undefined for a negative, but that's just going to be whatever use case you want for your function. So finally, let's go through and just see what is happening when I call this, when I call sum of 2. So we'll do one more of these heady little breakdowns, and I hope these things aren't too tedious, but I think they're a really good way to understanding what is really going on here. So when we call sum of 2, let me clear this out. When we call sum of 2, the first thing we do is create a counter. So counter equals 0. And then we invoke the inner function. And remember that because I've used this function declaration style, I'm allowed to invoke it above where I declare it. So down here, it's declared. We're not going to worry about that. But up here, we call inner function of, we want our start value, so inner function of 2. So here is a function call. Now within this function, we have our if statement, of course. So our if statement is first going to be false because 2 is definitely not less than 1. And then we increment our counter. So now counter becomes I plus counter, which is going to be 0 plus 2. And notice that because we have a closure with this counter up here, that it's actually this variable up here that's being changed. So not only do we change it on that level, but we also change it out here because of closure. So we're still within this function though. And next we're going to recurse. So we call inner function of 1. Within this, we check our if statement. It will be false. We update our counter. And once again, we have a closure with this counter out here. So we do 1 plus 2. So we get our counter up to 3. And that occurs both within the recursive function and also in this outer function because of closure. These variables are the same thing. And then, of course, we recurse one more time. So we recurse on inner of 0. Within this one, our if statement is true. And that means that we return. So we'll return pop out into this function. There's nothing left to execute, so we pop out into this function. And then finally, we pop out of our inner function into sum. So within sum, we see that counter has been incremented all the way up to 3, and we return our counter. So in that way, we're able to get up to 3 using this closure that we've created with this counter variable. So that is one technique for using recursion to generate return values, is you create an inner recursive function that actually does the recursing, and make sure you remember to call it, unlike me. And then you create a variable called counter or someplace to store info that's in our outer function. And that way we can use a closure to make sure that no matter how deep we recurse, we're still dealing with the same variable so that we have something consistent to return at the end. So let me go over just a few more use cases for this. So everything we've seen so far is something we could accomplish with a for loop. The 2 examples I gave you, you could write using a for loop. And to be perfectly honest, if I actually had to write either of these functions for work, I would use a for loop. It is a simpler way to approach these. Recursion is kind of fun and kind of crazy, but if you're just looping, probably want to use a for loop or a for each loop. However, there are cases where recursion becomes extremely important. And the best example I have is a tree structure. So let's say that you had some sort of object or array that's nested. So I'll do an array for you. So nested array. So we're going to have this array, and within it, we have arrays. And this is something you haven't seen so far, but it is totally valid, which is putting arrays in arrays. And maybe those arrays have arrays in them. And this one has an array in it, and et cetera. And maybe there's even an array in that one. And then at the most bottom level, there are some numbers. So we have this crazy tree-like structure where there are arrays nested in arrays in kind of this chaotic, unpredictable way. What if we wanted to write a sum function which added up all the numbers in here? We could do it without recursion if we got very clever, but it's extremely difficult to iterate through this type of nested tree-like structure where things are tucked deeper and deeper within it. It turns out that arrays are perfect for, recursion is perfect for this kind of thing. So the most common use case of recursion is going to be in these nested structures. So we won't get into an example of how to write that code because it's a little more advanced. But I will say that the DOM, which is something we're going to learn about tomorrow, is nested. So I'll show you another, even though we won't get into recursion tomorrow, I'll be able to show you another example of a type of situation where we probably would use recursion. So this becomes really important when it comes to decision trees. So for example, if you were writing an algorithm, if you're writing an AI chess player, you would have to deal with decision trees. You would want to consider, okay, if I move my queen here and then move my bishop here, what would happen? Well, what if I move my queen there, but then move my rook somewhere else? And those types of different, tree-like structures are really common, especially in AI, because you end up with these decision trees. And recursion is super critical for that. So while the examples we saw today could be accomplished pretty easily using a loop, it's important to get a hang of recursion because you'll start to encounter these decision trees or nested arrays or objects in which recursion will become a really big tool. So that is all I have for you guys tonight. Once again, I want to thank you guys for bearing with me at the beginning. I'm sorry about the technical issues, and I'm glad we were able to get them resolved. Does anyone have any questions for me on recursion? And while we're waiting for those questions to come in, I also want to mention that once again, for the homework tonight, we have just a couple problems for you guys to do, but they are more advanced. So definitely, if you feel like you're taking a long time to do each of them, that's not surprising. They are designed that way. Oh, I see a couple people typing, so let's see what they have. Okay, good question. So one of the questions that I think originally came from the actual YouTube Hangout is, does recursion ever work without using an if statement within the function? And yes, it actually does. I'm trying to think of a simple example of this. So I'm going to create a little tree-like object for you. So this thing is going to have so think of this as a family tree. So I will do my family. So we'll go ahead and do my mom's name, and then she has 2 children, my brother and me. So this is one way we could think of a tree, but the thing is we want to also know some information about me and my brother. So this is where things become nested. And once again, this is what I'm showing you here is a more advanced recursion case. So if you don't totally follow it, I wouldn't worry about that. But I do want to address the question because I think it's an interesting case. And if anyone's curious, here is an example of where recursion becomes really useful. So now each of these is going to be the same kind of nodal structure where we have, and my brother does not have children. And I also do not have children. So let me break down what's going on here. So we have this kind of node-like structure where we have a name and an array of children. And so for my mom, she has 2 children. So there are 2 items in this array. One for my brother and one for me. And they're of the same structure as her, except that both of our children arrays are going to be empty. So we could use recursion to iterate through this. So for example, if we wanted to log children, let's say we have a recursion function that takes in a tree. So what we would do is we would, or we can just say log family. So it should log everyone, including the children. So we could do console.log tree.name. And then I'm going to use a for each loop here. So children.forEach. And I can actually just pass log family directly in here. So there's a lot of stuff going on here. I'm really synthesizing a lot of the things that you've just learned how to do. So essentially what I'm doing is I'm iterating through each child, and every time for each child, I'm going to actually recurse. And you know what, let me do this in a for loop just to make it a little clearer. Equals tree.children.length plus. And then in each case, I want to do log family on tree.children at I. So I know I'm writing this kind of fast. I'll explain some stuff in a minute. So if I then run log family on this tree I have up here, where is, somewhere there is a comma. It doesn't belong. Oh, that doesn't belong. Okay, so we went through and logged everyone. First of all, as a breakdown of what actually is going on here. So what we're doing is we pass in a tree, we log the name, and then we loop through all the children and we recurse. So now for each child, we go through and we log the name again. So why doesn't this case need an if statement? Well, the reason is that the for loop basically works as a breaking point. So we only recurse if there are items in the children array. So because in the case of myself and my brother, there are no items in the children array, this never runs. So there is still kind of a base case, but it's not explicitly written. So the for loop will not execute. This line 12 will not execute whenever a child has no, or whenever a tree node has no children. So in that way, it'll dead end out whenever we hit these empty arrays. And notice that if I did have a child, now we're going 3 layers deep, but it still runs and my fake child still appears because we recurse 1 layer deeper, but then it quits when we hit this empty array. Okay, so I know that was a long answer to the question. I'll stick around for a few more minutes and answer a few more questions, but I am glad we got this out. Once again, I don't expect you guys to fully comprehend what's going on here, but if you're starting to get it and you want an example of something more advanced, this is how recursion actually usually plays out in the real world. So we have another question from William. And he asked, if we need to do something after the recursion occurs, where in the code will we place it? After the recursive function, but before the return statement? Yeah, William, that is exactly correct. So let me bring back a simpler recursive example. So I'll write out that countdown function again really quick for you guys. So we have our base case, turn, and then we console log our value, and then we recurse. So, and I'm just going to put a literal return statement in here. As a reminder, you don't need to put a return statement if you're at the end of the code, because it will return when it hits the end of the function. So if you wanted to do, so his question was, where would you put it if you wanted to do something after recursion? And the answer is just immediately after this line. So do something after recursion, you write that logic immediately after the countdown statement or whatever the recursive call is. And yes, if there's a return statement, it must come before that. If there's no return statement, it just needs to come before the end of the function. So if we put here, and then let me call countdown on start. So we have, so this line, hey, runs 4 different times because, or sorry, 5 different times, because we go through this 5 times, we recurse 5 times, and then we pop back out, and this line will run 5 different times. All right, I see we have a couple more people typing. I'll stick around for a few more minutes, so if you have more questions, definitely keep asking. All right, Slack has gone quiet, so I think that, oh wait, we have one more question. So Sebastian asks, why doesn't it work if we change the return statement to a break statement? All right, so let's try that out and see what happens. Will it work? What do you guys think? So we got an error, unsyntactic break. And that's because break statements are not designed for functions. So they do something similar to the return statement, but it's just the context is different. So if you ever want to quit out of a function, you always use return. Whereas break statements tend to be used for, actually I haven't used a break statement in a really long time. I believe they're used for for switch statements, which are kind of like if statements, but honestly, no one uses switches in the real world. So yeah, so if you ever want to break out of a function, it's just that return is the correct keyword for that. Let's actually Google breaks. I want to make sure that I'm giving you guys the full story there. And oh, yeah, we use them in for loops as well. That's right. My bad. So if we have a for loop and we want to quit it at some point, so let's just do a little for loop. Oops. So if anyone is not familiar with a break statement or hasn't used one in a really long time like me, let me show you how they work. So let's say we have this loop that is just logging our index up through 10. But if for some reason we just really hate the number 4 and we don't want to log 4, we could do if I equals 4. And this is working really similar to how we saw that return statement working, in that it's just telling the for loop to quit. So at this point, it will stop when it hits 4. If instead we want it to skip 4, but carry on looping, we would do continue. So in that way, we log all the way up to 9, but we skip 4. So breaks and continues. Breaks stop a loop altogether. Continues just say, hey, go to the next iteration. Versus a return statement, which is going to be used in a function to do something similar. All right. Well, I think that that is all the time we have for tonight. So 1 second. All right. Once again, thank you so much for bearing with me tonight with the technical difficulties. I hope you guys are starting to wrap your head around recursion. If you're struggling with it, maybe go out and buy some Russian dolls and it'll all start to make sense. That is it for tonight. We have one more lesson tomorrow. As I mentioned, we have a couple of homework assignments. We are getting into some pretty advanced territory here, so definitely use the resources. Reach out in Slack. Do any Googling you can, and feel free to go back through the video to review what I covered tonight. Thank you guys again, and I will see you tomorrow for our final lesson. Have a great night.